Q3 is equal to 0. This, of course, is absolutely a fantastic result. This is a very pleasant way to look at the composition of quadratic forms, much in the same way as you construct a group law on elliptic curve, right? When you have an elliptic curve, then the addition is you say that these 3 points together give you 0. And then the inverse is some obvious operation, right? The symmetry.
Obvious, but we can construct a cube which gives Q1 and Q2 fixed.
Yeah, of course. If you have any 3 forms, Q1, Q2, and Q3, then there is always a cube such that the corresponding forms are Q1 and Q2. This is a bit of a difficult thing to process right now. Let us not stop on that. Let me explain how this is done. So we can assume that the greatest common divisor of all our numbers is equal to 1. Then use an action of SL to Z times SL to Z times SL to Z. You can ensure that this element is equal to 1. Then using SL to Z once again, you can make these adjacent elements to be equal to 0. And then you get a cube 1, 0, 0, 0, D, G, H, F. And then you can explicitly check that the corresponding 3 forms will be in composition. Let me write down the explicit forms here. Forms will be minus dx squared plus hxy minus fgy squared. You also get minus gx squared plus hxy minus fdy squared. And you also get minus fx squared plus hxy, plus, no, this cannot be true, sorry, dh minus fg. Plus fg, plus fd, plus dg y squared. And you can explicitly check that the product of these 3 forms in your class group is actually equal to 0. This is, of course, very fun. But this does not give anything new or interesting, right? It is just a rephrasing of the composition. But Bhargava was inspired by this observation, and he actually defined a composition on the cubes themselves. So if you have 2 cubes, you can take a composition. And when he considers cubes with different symmetries, then the composition of corresponding cubes will correspond to some very nice operations on cubic forms and some other stuff. Okay, so that's all I wanted to say for today. Thank you very much for your attention. I hope that if we have enough time after we finally prove the Gauss class number problem in several ways, we will also have time to discuss Bhargava structures a bit more. Thank you very much. Do you have any questions? Maybe. Also, I forgot to say about genera. Actually, the set of genera corresponds to the 2 torsion of the class group. So actually, genera are in bijection with two torsion. This means that ideal numbers are just numbers such that every element in class group multiplied by 2 is equal to 0. Huh? So you had a question? I cannot really tell you now because I don't really understand the.
Class group is not an arbitrary abelian group.
Yeah, class group is of course not an arbitrary abelian group. It is conjectured implied by the ideal number conjecture that it cannot be equal to z over 2z to the power 5. You can probably check it independently because there is a list of all number fields or all imaginary quadratic number fields with class number at most 100. So I don't really have a quick answer about the composition of cubes, but if you want to, we can return to this topic somewhere later in the course.